This is Babitha, working as Assistant Professor in the Department of EC in Institute of Aeronautical Engineering. In this session, we are going to discuss about the different resistances which are existing in the operation of the diode, as well as breakdown mechanisms in the diode. So, while coming to the contents, just what is the diode static resistance we are going to discuss. It will become in the forward characteristics of the diode, and what is the dynamic resistance of the diode, and next what is meant by avalanche breakdown and what is meant by Zener breakdown in the case of PN junction diode. So before going to the different static and dynamic resistance of the diode, first of all we have to know the function of the diode. Then only we can able to estimate the values of both the resistances from the diode. So in order to design the PN junction diode, we require two types of materials. One is the P type of semiconductor material and one is the N type of semiconductor material here. And I have already mentioned in the previous sessions, the P type semiconductor material is having more number of holes compared to the electrons. So that's why in the case of P type of material, we are indicating with the plus symbols here. Along with this, we are also having some number of or some few electrons here. Okay, and in the case of N type of material, so this is the extrinsic type of material. To make this N type of semiconductor material, we have to add the pentavalent impurities to the intrinsic semiconductor material. So if we add the pentavalent impurities, we are having more number of electrons in the material. So that's why we are indicating with the negative symbols here. And in the N type of material, more number of electrons are present compared to the holes. So that's why only few holes which are present along with these electrons. So in order to make the PN junction diode, we have to take one small piece of P type of semiconductor material and one small piece of N type of semiconductor material, and if you join the two materials together, then it is formed the PN junction diode like this. So it is the here when we add or when we join the two P and N type of materials, the PN junction is formed here. Okay, so as soon as when we join these P type of material and N type of material, the holes which are present in the P type of material are trying to diffuse or move towards the N type of material. So once this hole which is trying to move towards the N type of material, and it will try to combine the electron which is present in the N type of material. So once this hole leaving its space and combine with the combine with the electron means it is having the positive immobile ion. So this in the N type of material is forming the positive immobile ion. And similarly, the electrons which are present in this N type of material are trying to diffuse or move towards the P type of material here. Okay, so once this electron is trying to move from this N type of material and combine with this hole, it will become the negative immobile ion here. So because of this diffusion of holes from P type to N type and electrons from N type to P type, near the junction more number of positive as well as negative immobile ions will be present here. So across the P type we are having more number of negative immobile ions, and across N type of material we are having more number of positive immobile ions here. So this indicates that these positive and negative immobile ions indicates the depletion region here. Indicates the depletion region of the PN junction diode. So because of this forming the depletion region across the junction of the PN junction diode, the charge carriers are not moving from P to N and N to P. Why? Because the P type is having negative charged ions. So this electron is having again negative charge. So these are repelled by these negative charged particles, and these holes are repelled by these positive charged particles. So this depletion region acts like a depletion, or like a wall between the major charge carriers between the p type as well as n type of materials. So this depletion region is also we can indicate with the battery negative terminal and positive terminal. Why? Because this side we are having the positive charge and this side we are having with the negative charge. So this potential we are calling it as the barrier potential. Why? Because depletion region acts like a barrier between the P and N materials. So in order to activate this particular device, so this is the situation occurs whenever we are not applying any voltage to the diode. When we are not applying any voltage to the diode, because of the diffusion of the charge carriers between the p-type material and n-type material, we are getting the equilibrium state in the p-n junction diode. That is nothing but equal number of holes as well as equal number of electrons which are present in the p and n type of materials. So in this particular condition, or in this particular case, there is no current which is flowing in the device. So in order to make this device into conduction, or to make it as active, we need to provide some input voltage to the device. So to provide this input voltage, we are having two conditions here. That is nothing but biasing. We need to provide the bias for the device to activate this. So this particular bias, we are having two types: forward bias as well as the reverse bias of the diode. So when we go with the forward bias of the diode, so in the case of forward bias of the diode, we are taking the PN junction diode with the P type of material and N type of material, and here having so many holes and less electrons, and here we are having so many electrons and few holes. So when we add the source, that is positive terminal to the P type of material and negative terminal to the N type of material. So it is the VF voltage or forward voltage we are applying to the diode. And here we are also having the depletion region. Okay, here we are having the barrier potential VB also. So the voltage we are providing for the the voltage we are providing for the diode is more than the barrier potential which is present across the junction of the diode. In that case, the diode will enter into the forward bias condition and there is a flow of current in the device. So what will happen here, it is exactly is the positive terminal of the battery. So the holes, the majority charge carriers in the p type of material are repelled by this positive terminal. That is nothing but they are not coming here, they are moving towards the junction here. And similarly, the electrons which are present in the n-type material are also repelled by this n-type of material, and these are also moving in this direction. So the movement of holes as well as electrons are towards the depletion region. If we increase this particular voltage, the force will be increases. More number of electrons from this side, holes from this side are trying to push towards the depletion region. So now, because of that force, these electrons will enter into this uh, depletion region, and this will combine with positive immobile ion and it will become the neutral state, or it will become the normal negative charged particle. And similarly, these holes combine with these negative charged particles and these are becoming the positive ions here. So because of this movement of charge carriers towards the positive direction as well as the negative direction, or towards the p type of material and towards the n type of material, the large movement of charge carriers will be done in the case of device. So there is a flow of current in the device. So in this case, the electron flow is in this direction, so the current direction is in this direction, I. So in this forward bias condition, we will get like this. So in the forward bias condition, if we see the characteristics voltage versus current characteristics of the diode, we will get like this. This is nothing but V gamma R cut-in voltage. So once applied input voltage is, or forward voltage is greater than this cut-in voltage, at that time there is a sudden rise in the current. Till that time there is a very less variation in the current and very less increment in the forward current. So these are the characteristics or forward characteristics of the diode. And similarly, if we see the reverse bias. So reverse bias means the negative terminal of the battery is connected to the positive terminal and the positive terminal of the battery is connected to the negative side of the diode. That is nothing but, again I am taking, this is p type of material, this is n type of material. It is having more holes and less electrons, and here we are having more electrons and less holes here, and it is forming the junction with negative charged particles and positive charged particles here. And in this case, I am providing the positive terminal here. Sorry, very sorry, it is reverse bias. It is the negative terminal of the battery is connected here and the positive terminal of the battery is connected here. Minus plus, we are applying the reverse voltage. So when we apply the reverse voltage to this, what will happen, we'll see now. So the majority charge carriers of the p type of material, those are holes, are trying to move towards the negative terminal of the battery. Okay, and the electrons from this n type of material, the majority charge carriers in the n type of semiconductor material are trying to move towards the positive terminal of the battery. So the movement will be like this here. Okay. So the electrons as well as holes are coming away from the junction here. Because of that reason, the depletion region width will be increases very high here. The depletion region width will be increases here. It is increasing very high. So once the depletion region width is increasing, means the number of charge carriers movement will be decreases. So once the number of charge carrier movement is less, means it is the zero current will be flowing in the device in the ideal case. But in the practical case, very small amount of reverse saturation current will be flowing in the diode here. So in this case, the electron direction is in this direction. Okay, so the reverse current will be flowing in the here the electron flow is in this towards the junction, so the current direction is here, P to N. So in this case, the current direction is from N to P, that is the reverse current direction is into P here, that is opposite to the electron flow here. Okay, so in this reverse bias condition, we will draw like this. It is the reverse voltage minus we are applying, and we will get the reverse current also in negative form. So we will get like this. So initially it will increase very slowly and it will maintain that constant value. So once, because of the accumulation of more number of charge carriers across the junction, there is a breakdown occurs in the device. So at breakdown voltage, there is a sudden rise of this reverse current. Actually, this is not required to us. Actually, we are going to utilize this diode in the forward bias condition only. We are not going to utilize in the reverse bias condition. So that's why we have to maintain the minimum reverse voltage to operate in the proper way. Okay. So once the breakdown occurs means the large amount of reverse current will be flowing in the diode so that it may cause damage to the device. So the symbol for this diode we will indicate with like this. This is P and this is N and this arrow indicates the direction of the current in the device. Okay. This is the PN diode operation. So why we discussed about all this PN diode construction and operation means in order to calculate the static resistance as well as the dynamic resistance of the diode here. So while coming to the diode static or DC resistance here. So from the forward characteristics of the diode, we can able to find this static or DC resistance. So this static or DC resistance indicates the resistance of the diode at a particular operating point is called the DC resistance. So here, for example, I am taking this particular point as the operating point of the diode. We can take anywhere, either here or here, anywhere. So at this particular point, how much amount of voltage we are applying and how much amount of corresponding current it is flowing device. So this voltage, from this voltage and from this current at this point, we can able to find the value of DC or static resistance. Okay, so the resistance of the diode at the operating point can be found simply by finding the corresponding levels of VDI ID here. So it can be determined by using the ratio of voltage to the current, diode voltage to the diode current here. So the lower current through the diode, the higher will be the DC resistance value, because the resistance is inversely proportional to the current here. So that's why if the current flow is very high means the static resistance value is very less here. So in the case of forward biased PN junction diode, the DC resistance value is very less. But in the case of reverse biased diode, the DC resistance value will be very high. Why? Because in the forward biased condition, there is a high flow of forward current in the device. But in the reverse bias condition, there is a low flow of reverse current in the device. So that's why resistance value is very high. So that's why from the forward characteristics of the diode only we are going to calculate the DC or static resistance. Static means it is not varying here, but with some fixed point, at some fixed point only we are calculating the values of voltage and current. From that values only we are going to calculate the resistance value here. And next diode dynamic or AC resistance here. So here dynamic means variation here. And we are also calling it as AC resistance. Why? Because in this case when we apply the AC voltage to the diode, how much amount of current it is going to generate. So for that purpose, here actually static resistance is the DC resistance using DC input, but the dynamic resistance when we apply the sinusoidal signal to the diode, how much amount of current and voltages we are getting. If we calculate the resistance by using that corresponding voltages and current, that particular resistance we can call it as the dynamic resistance. So the resistance determined by a straight line drawn between the two intersections of maximum and minimum values of input voltage here. That is nothing but the input voltage we are providing here, it is this much. This is the maximum value and this is the minimum value. And the corresponding output current we are indicating like this. This is the maximum current value and this is the minimum current value here. Okay, so the differences between this maximum and minimum value will give the del ID value, and the differences between the maximum voltage and minimum voltage will give the del VD value. And to find this AC resistance, I am taking dou VD by del ID. So we can also call it as, we can also write it as V maximum minus V minimum by V maximum plus, I maximum minus I minimum values. So from this we can able to find the dynamic resistance of the diode. So in order to calculate the dynamic resistance of the diode, here we need to note the diode current equation here. See, static resistance we are calculating at one particular point of the VA characteristics, but the dynamic resistance is varying here. So in order to see that variation, how much it is showing, that we can calculate from the diode current equation. So how we can get this diode current equation? So the diode current equation gives an expression for the current through the diode as a function of voltage. So from the ideal diode law, we can express this current as I naught into e power v by eta vt minus 1, where this I naught is nothing but the reverse saturation current in amperes whenever we are applying the reverse bias or reverse voltage to the diode. And V is nothing but the applied voltage, that may be in the forward bias condition or reverse bias condition. If it is forward bias condition, we have write it as Vf. If it is reverse bias condition, we can write it as Vr here. And eta is 1 for germanium diode and 2 for silicon diode. This eta indicates the quality factor or quality of that particular diode. And Vt is nothing but the voltage equivalent of temperature in ohms. And Vt equal to Kt, we can write that is K is nothing but the Boltzmann's constant. The value of that one is 8.62 into 10 power minus 5 electron volts per degrees Kelvin here. Okay, so this temperature we can measure in degrees Kelvin here. So generally this Vt value is 26 millivolts. We will take at 300 degrees Celsius. At 300 degrees Celsius, the value of Vt we will take it as 26 millivolts. And so this is the equation, PN junction diode current equation, I equal to I naught V by eta Vt minus 1. So depending upon the temperature variations, this value will be varying here. And depending upon the eta value also, this will be varying here. And the V value may be either the forward voltage or reverse voltage we can apply here in the case of PN junction diode current equation. And if you find the expression for the dynamic resistance of the diode, I am going to utilize this diode current equation here. So in the diode current equation, we have taken it as I equal to I naught into e power v by eta Vt here. So here the dynamic resistance is the reciprocal of the slope of the VI characteristics of the PN junction diode. So for the incremental change in the voltage, there is a corresponding incremental change in the current. So that's why the dynamic resistance of the diode R, I am writing here it as 1 by slope of graph. So that graph is between the voltage and current here. That is nothing but 1 by di by dv. K1 by di by dv is the slope of the graph. Okay, so now from current equation we can write it as current equation we have taken already, it is I naught equal to V by Vt minus 1. So this one take it as the 1 and this is 2 here. So from 1 I am writing here, I am differentiating this current equation I with respect to V here. So I will get it as di by dv is equal to I naught is the constant I am taking outside, that is V by eta Vt into e power V by eta Vt. The differentiation of constant 1 is 0 here. So I can write it as I naught e power V by eta Vt by eta Vt here. So this is the third equation I am taking. This is the third equation I am taking, that is the value of di by dv. K value of di by dv. So now from this I can write the value of dynamic resistance or RAC equal to 1 by di by dv. That is slope. That is nothing but 1 by I naught e power v by eta vt divided by eta vt. So this value is eta vt by I naught e power v by eta vt here. So this is the value of dynamic resistance or AC here. So but from the current equation we can also write it as, that is nothing but from first equation I can also write it as I equal to I naught into e power v by eta vt minus I naught here. So I can write it as I naught e power v by eta vt is equal to I plus I naught. So here I plus I naught I am taking here it as the, this is fourth equation and this is fifth equation. So now substitute this phi in fourth equation. So if we substitute like that, RAC is equal to eta vt by I plus I naught. So this is the value of the RAC resistance. So the value of RAC resistance, to calculate the value of RAC resistance, we can use either eta vt by I naught e power v by eta vt, or we can also utilize eta vt by I plus I naught. That is, depending upon the given values in the problem, we can utilize either this formula or this formula in order to calculate the dynamic resistance of the diode here. So the static resistance anyway we are taking directly from the diode at one particular point. And till now we have seen the different resistance values of the diode here, and now we will see the different breakdown mechanisms which we can expect in the case of semiconductor diode. Here, when we apply the reverse voltage to the PN junction diode, we are getting the depletion region. High amount of depletion region is forming across the junction here. So the high amount of depletion region is nothing but more number of positive and negative immobile ions are accumulating near the junction here. So more number of positive and negative immobile ions are accumulating near the junction means that will cause the damage to the device here. So these breakdowns are of two types. One is the avalanche breakdown and one is the Zener breakdown here. So now we are going to discuss about the avalanche breakdown. So generally this avalanche breakdown will occur in the thinner regions of the depletion region. So here the depletion region is very thinner, means that the doping level of the device is very high. Once the doping level is very high means the number of impurities are very high, the number of majority charge carriers are very high. So once the number of majority charge carriers are very high in the device means definitely the depletion region width is very less. So in this breakdown, with the electric field is applied across the diode, the velocity of the charge carriers increases. So in this kind of diodes, whenever we are having thin depletion region diodes, when we apply the voltage to that, it will create more number of charge carriers. So once the more number of charge carriers are increasing means these charge carriers will collide with the other atoms which are present in the device, and those are creates the new pair of holes and electrons here. So because of that collision or recombination process, more number of more number of negative and positive charge carriers are accumulating near the junction. So once because of more number of charge carriers are accumulated means, and again these free charge carriers again further collides with other atoms and creates more pairs of electrons and holes, which is called as carrier multiplication. So because of this application of the electric field to the thin depleted region PN junction diodes, more and more number of free charge carriers are accumulated near the junction, so more number of carriers are improved here. So these free electrons are start moving across the junction. So these are forming in the depletion region now, but they are trying to move diffuse the towards the junction. That is nothing but electrons from N region to towards the junction, and holes from P region towards the junction here. So a junction and develop the reverse bias current here. So those will develop the reverse bias current here. So this reverse bias current completely destroys the junction here. So this is called as avalanche effect. Avalanching is nothing but a collection of or accumulation of more number of charge carriers. And the mechanism of destroying the junction is called reverse breakdown of the PN junction diode. So the voltage at which the breakdown occurs is called the reverse breakdown voltage of the PN junction diode. So once this junction breakdown occurs, it cannot regain its into its original position here. Once the breakdown occurs means we cannot again make it as the normal device here. That will destroy the device here. So actually this due to this avalanche breakdown, so this because of this breakdown voltage we are getting the avalanche effect. Due to this avalanche effect there is a sudden rise of this reverse current IR here. Sorry, this is IR and this is VR. Because of this, actually in the case of avalanche breakdown, it is generally coming to the thin depleted regions PN junction diode. Why? Because the doping levels in this case is very high. So though it is having very thin depleted region, in this case once we apply the reverse voltage gain, the more number of charge carriers will increase in the device. That charge carriers will combine with the other atoms which are present in the device, and that will again combine with the remaining atoms, and that will improve more and more number of charge carriers. That indicates the carrier multiplication. So once because of this more number of charge carriers developed across the junction, those are moving towards the junction and there is a chance to break down the junction here. So once the junction is breaking down means there is the device is damaged here, we cannot utilize for any other things. So in order to overcome this avalanche breakdown effect, we have to maintain very less amount of voltage we have to apply for the PN junction diode here. And next type of breakdown, here we are applying, here it is. So here we can expect in the PN junction diode is the GNR breakdown here. So this GNR breakdown mechanism will occur in the heavily doped thin region is called GNR breakdown here. Okay. So here it is, in this case it is appearing for the thinner regions, it is appearing for the heavily doped regions is called GNR breakdown. So once we take one PN junction diode with heavily doped, so once the PN junction diode is heavily doped means the depletion region width is very narrow here. So the depletion region width is very narrow means the electric field across the depletion region is very intense. So under the reverse bias condition. Okay. Under the reverse bias condition, the electric field across the depletion region is very intense under this reverse bias condition. So an intense electric field enough to pull the electrons out of valence band to the stable atoms here. So this intense electric field whatever we are generating across the junction will pull all the electrons out of from the valence band, and that will enter into the conduction band, and those are ready for the conduction, but those are coming due to the reverse voltage here. So these electrons constitute the heavy current in the reverse direction. So in Zener breakdown, the temporary breakdown of junction occurs. So the junction regain its original position whenever we remove the reverse voltage to the device here. So in this particular case, this will occur early here. Why? Because it is having very less, very thin depletion region. So this is occurring due to the Zener breakdown. Here we are applying the negative voltage and we are getting the reverse current. There is a sudden rise of reverse current due to the Zener breakdown. Always avalanche breakdown will appear for the lightly doped PN junction diodes, and the Zener breakdown will occur in the heavily doped PN junction diodes here. So because of the less or thin depletion region, once we apply the reverse voltage to this, it will improve more number of charge carriers, and because of this reverse voltage application of the diode, it will pull all the valence electrons from the energy band structure of that particular material, and those will move to the conduction band to conduct the device. So those are ready to conduct means that will break the junction here. But before that only, if we remove the reverse voltage from the diode, we can able to reduce this Zener breakdown, and we can able to make our device in safe mode. But in the case of avalanche breakdown, we cannot regain it into original position. But in the case of Zener breakdown, once we remove the reverse voltage, we can able to make it into the original position here. So in this way, anyways, the both the breakdowns are not required in the PN junction diode. Once we maintain the proper normal less reverse voltage for the PN junction diode, in that case we can able to reduce the effect of this avalanche breakdown as well as Zener breakdown. So once we maintain the less reverse voltage, and anyway we are going to operate the diode in the forward bias condition only in order to operate it as the active device or normal device. Always in the forward bias condition, we can utilize for the switching application. We can utilize in the on switch for the forward bias condition, off switch in the reverse bias condition. And these are the differences of the avalanche breakdown as well as the Zener breakdown. So this avalanche breakdown is a phenomenon or increase in the free electrons or electric current in the semiconductor and insulating material by applying the higher voltage. So because of applying the higher voltage, the Zener breakdown will occur, the process in which the electrons are moving across the barrier from the valence band of P type of material to the conduction band of the lightly filled N material is known as the Zener breakdown. So the movement of the charge carrier from the valence band to the conduction band, this is occurring here, and this is due to the application of high voltage to the device we are getting here. And the depletion region is very thick in this case. It is very thin. Why? Because it is heavily doped. It is lightly doped. The junction will destroy whenever you increase the reverse voltage here. It is not destroy when we remove the reverse voltage here. And the electric field is very weak here, and it is very strong in the case of Zener breakdown. And the doping is very low in this case. It is very heavy in the Zener breakdown. Because of this reason only, this is thick here and this is thin here. And the temperature coefficient, that is the positive temperature coefficient for the avalanche breakdown and the negative temperature coefficient for the Zener breakdown. Ionization, because of collision process, ionization is occurring here. Because of the electric field, the ionization is occurring in the breakdown, Zener breakdown. And here the breakdown voltage is directly proportional to the temperature here, and here it is inversely proportional to the temperature. Why? Because it is having negative temperature coefficient. And after breakdown, voltage will vary here, but in this case voltage remains constant after breaking the junction. Why? Because we are removing the reverse voltage once it is entered into the breakdown condition. So these are the differences between the avalanche breakdown and the Zener breakdown. So in this session we have discussed how to calculate the static and dynamic resistance of the PN junction diode, and how the avalanche breakdown will occur, as well as how the Zener breakdown will occur in the PN junction diode, and how to remove the breakdowns we discussed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.